Well, we have one more objective before we finish this chapter, and you guessed it, it's applications. Now, we started the chapter with the really heavy-duty linear programming application. You haven't forgotten about that, right? But we're going to finish with what's considered a little more of just a standard traditional system application. So each of these problems is going to require us to set up at least 2 equations, perhaps 3, and then we're going to solve that system using either substitution, elimination, or you could even use the matrix method. Now I'm going to do 3 problems. Obviously you can see A, B, C. I just want you to know that I'm just trying to get you kind of in the mood, thinking about systems. Some of the problems that you're going to do on your own, yes, they will be similar to these, but there's also going to be some that are different. So we got to be able to think like a system, and these 3 problems are going to help us to start doing that. So let's begin. Letter A, we got a boat. Now it travels 210 miles downstream. I don't really like quite how this is worded. It also is 210 miles back upstream. So it's 210 miles each way. Looks like the downstream took 10 hours and going back was 70 hours. So there must be quite a current in this stream. It's also a really long stream. It's 210 miles long. We'll go with it. Now, what's the speed of the boat in still water, and what's the speed of the boat, or what's the speed of the current? So we've got basically the speed of the boat, like its motor speed, and we also have the speed of the current. Those are kind of like the 2 things that are unknown in this problem. And just like any good application problem, it's always where you want to start, with your unknowns. So it makes sense. Let's let B be the boat speed. That's actually how it's written in the paragraph anyhow. And we'll let C be the current speed. So B is the boat speed, kind of like by itself, and C is the current speed, kind of by itself. Now, a little bit of the trick to this problem is that there's definitely something as far as putting both of these speeds together. So we can start to make some additional statements where if you add these 2 speeds, the boat speed and the current speed pushing it along, that's going to be like how fast the object is going when it goes downstream. It's kind of like the overall speed downstream. But if you subtract these items, B minus C, well, that's going to kind of be like the overall speed going upstream. So we can actually take B and C and we can add or subtract them to kind of come up with, again, like an overall speed. Now, where's the equations? We need equations when we're doing application problems. I've got good news for you. It comes from a basic principle from science class where distance will always equal rate times time, right? You've heard of that little formula, distance equals rate times time. Well, what we're going to do is we're going to be able to use the distance that is being referred to in this problem. So this is going to be my downstream distance along with my downstream rate. What's my downstream rate? That's right, it's B plus C. So my rate is actually going to be a combination of B and C. And in my time, well, we just grabbed that out of the paragraph, was 10 hours. And all of a sudden, we have an equation. Now, the interesting thing is that we need another equation that's going to use distance equals rate times time again. That's because we still have the same distance, but we have a different rate. It's the rate when I'm going upstream. That's right, we're going to subtract these items. And then I need another time. Remember, it was at 70 hours. Well, I've got 2 equations. I know they look a little strange. They're kind of a little different, but I got 2 equations with 2 variables. And I promise this is a system. All we have to do is kind of make it look more like a system. We need to do a little bit of algebra. Excuse me. So I'm suggesting here that we distribute 10 to make this look like 10b plus 10c. Now that'll equal 210. And then we can do the same thing with 70, right? We can distribute that. Make this look a little bit more like 70 70b minus 70c, and that'll equal 210. Now that looks a little bit more like a system. In fact, I can even put a little curly brace around it. Do you believe it? If we solve that system, we'll be able to individually get b and c, even though we have a lot of the same numbers. It's going to work. Let's go to the matrix method to solve this. Pretty nice method, eh? Especially when you have some larger numbers. So it looks like I'm going to need a 10 and a 10 for my matrix A, 70, and a negative 70. And then my matrix B is going to have the same two numbers. Again, is this going to be okay? It is. It is. As long as we do the magic formula. Remember, the magic formula is A inverse, say it with me, A inverse times B. And out pops 12 and 9. What's 12 and 9? Well, those are like my individual speeds. And they would be in the same order, so that means that B is going to be my boat speed, 12 mile an hour, and C is going to be the current speed, 9 mile an hour. This is a good problem to check. That is to kind of check with, I guess you could say, some common sense. Common sense would say that if I add these two numbers together, I get an overall boat speed of 21 miles an hour. And 21 miles an hour for 10 hours, 21 miles an hour for 10 hours, bingo, that's going to be 210. If I subtract these, I get 3 mile an hour. 3 mile an hour for 70 hours, well, that's also going to be 210. It's going to also be really slow, but it works. Both these answers make sense. Now, there's one thing I didn't do. I should have did it, so I'm going to kind of backtrack real quickly here. I never really identified matrix A and matrix B. Now, what you see me doing right here, I'm going to give you permission to do. It's a little bit of a shortcut. I'm not a big shortcut guy, but if you feel like you have your system organized and you feel like that the numbers are easy to see, the coefficients are easy to see for A, and the constants are easy to see for B, then I'm going to allow you to put little brackets around and get her done as A and B. But I want you to show that. I want you to show at least that matrix work. All right, we're going to continue now with example B. Looks like we've got kind of like a little bit of a chemistry problem dealing with some mixtures and chlorine. Now listen, you don't have to be in chemistry to understand this problem. Really what's going on is we have a 5% chlorine solution. That's just like the strength. And then we have a stronger solution over here, a 9%. And we're trying to mix these together into a new cup, so we're going to try to pour them in, but the question really is how much of each do I pour in? Now, if you think about it, you want 8%, so there's a really good chance that you're going to want to pour more of the 9% and maybe just dilute it a little bit with the 5%. But the real question is, of course, how much really do we need to do of each one of these? It's a good system problem. So let's start, again, where all good system problems start. That is with your unknowns. And just like we said, we're trying to figure out how many liters of the 5% do I want to pour in, and how many liters of the 9%. So those are our variables. Now, if you look at the very first few words of this problem, Bob needs 3. Bob needs 3 is actually a simple statement about x and y. Literally about x plus y. Because all it's really saying is if I take a little x and I add a little bit of y, I'm going to want to end up with a total of 3 liters. So that's my typical, as I like to call it, my total equation, my total. But there's another equation. You know that it's going to involve these percentages. If you think about it, the 5% is always going to go with the x because that means you get 5% of the x. And similarly, the 9% is going to go with the y. I get 9% of the y. But you see, it would be a little strange just to say 8% by itself, because a percent is always of something. So what I need to do is I need to multiply 8% of the total. Now again, the total is 3, so we take 8% times 3, and that's going to give us actually the number 0.24. Now what 0.24 actually represents is how much chlorine I'm going to end up with in this solution. In other words, I'm going to end up with like a quarter of chlorine, a quarter liter. And the rest of it's just going to be water. All right, but that's getting a bit into the chemistry part, which is fine. But notice that now I have two equations and two variables, so that's a classic example of a system. One thing that I like to do with this problem is simplify it a little bit. It's easy for me to erase, and that's what I'm going to do. I'm going to get rid of that multiplication and just say that this equals 0.24. Matrices. Everybody likes them. I hope everybody does. But don't forget, just because we have the matrix method, don't forget about some of the older methods. Honestly, this problem could be easily solved with the elimination method if I just multiplied by a negative coefficient, perhaps just multiply by negative 0.05, so that your x's will be opposites. And it's really, again, not that hard. I know we have some decimals here, but you're just going to add those equations together, make those x's cancel. We're going to end up with some certain amount of y, I guess it would be like 0.04y, and we're going to end up with 0.09. And I know those are decimals, but you can divide them on a calculator, and that gives you 225. Now, that's pretty nice, because if you know that you need 225 of y, even though I'm erasing my cup diagram, we only need a little bit more of x, right? How much more of x do we need? We just need enough to get 3 liters. So that was pretty simple. Once I get my first answer, I know that both of them have to add to 3, or I could just plug it back into this equation and get the same thing. Now, when you're doing a word problem, you really should label your answers. So, I did label as x, but perhaps even better yet, I could say 0.75 of the 5%, or even better than that, I could say 0.75 liter of the 5%, and then 225 liters of the 9%. So I can get a little bit more of a label to my answer, just to make sure that I'm sure that I'm right. All right, one more system, one more word problem that's going to turn into one more system. Just take a quick look at that. Looks like I got 500 tickets for a concert. Tickets for adults are $7.50, children $4, senior citizens $3.50. And then the total amount of money that was made was $3,025. Then we get in some fancy math, twice as many adult tickets as children. How many of each? How many of each? Well, that's where we start. Remember, we start with what we're trying to find. And this would be a perfect time to decide how you're going to set up X, Y, and do you realize Z? X, Y, and Z. We've got 3 different types of tickets. Now, it really doesn't matter which way you put this, but I believe this is the way it's written in the paragraph, even though it's not actually sort of chronological. We'll stick with this. Feel like you can write some equations? Well, just a heads up, you're going to need 3 equations. That's because you have 3 variables. Now, one of the equations is, you guessed it, the total equation. X plus Y plus Z. Add them all up, right? The total amount of people that went to the concert, 500. That's your total basically attendance. But we also have like a total revenue, right? You get revenue. You get $7.50 for every X. You get $4 for every Y. So we have like the classic multiply equation, where you're multiplying each variable by its value. And that's going to give us our total revenue. Now there's one more equation that's left. It's the one right here The one right here, it says twice as many adult as children. Twice as many adult as children. I want you to think about this with me for a second. Twice as many adult as children. Does that make sense? Or how about twice as many adult as children? Does that make sense? Uh-oh. You got to realize only one of them can be correct. It's not like we could choose either one. Which one makes sense? Now, this is sort of the age-old dilemma of this statement, twice as many. We all know what twice means, but let's think about it. That means that the adults are the larger ticket, right? If twice as many adults were sold, then there's more of these. This is the larger number. That means the children is the smaller number. Now, if you agree with me that the adult, or X, is the larger number, then which equation makes sense? Does it make sense to double a large number X, and get a smaller number Y? Double a large number, get a small number. Sounds kind of weird. Or does it make sense to double a small number to get a larger number X? To double a smaller number and get a larger number X, ding, 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 that's the one that makes sense. So this is going to be the equation that we keep, and this other one over here gets thrown out. Now, be careful that you interpret statements such as twice as many correctly. And again, all I really did, kids, was just think about which number was bigger and smaller. Now, this equation down here is, well, it's a little bit disorganized, isn't it? It just doesn't feel right. So do you want to subtract X? You should. You should move X over to the other side. And I'm going to leave the 2Y where it is, but now the equation's equal to 0. That's okay. It's allowed to equal 0. Also, it's still slightly out of order. I really should have the 2Y in line with the Y so that I have a vacant spot right here. What goes in that vacant spot right there? That's right, another 0. Because if you're feeling like using matrices, we need to make sure that we have 3 numbers in each row. So I need that 0 filling in that last spot. Do you want to use matrices? It looks pretty straightforward. You got 1, 1, 1. You've got the dollar amounts, and then you got -1, 2, and again 0 that we filled in this spot. So I'm thinking that matrices would make quick work of this problem. Let's get her typed in. What happened? My screen's all zoomed in. Okay, that's not going to work. Let's try that. Well, not really sure what I did, but I think that I can see all my numbers. Notice that I'm making this a 3 by 3. I'm going to go ahead and do the work of typing these numbers in. I hope you're not just watching me do it. That's no fun. Make sure that you're comfortable typing them in. And especially the last row, remember what I did. I got to remember what I did. I subtracted X. So now I have a -1. I also have a 2 on the Y. And 0, 0, 0 for that last placeholder. And then I believe I need to up this one so that I can fit 500, so that I can fit 3025, and so that I can fit 0. Yep, that's all right. There's going to be a 0 there. Okay, A inverse times B takes the cake. And I've got, I hope, my 3 answers for ticket sales. Now, I say I hope because you can always check them. You can always check them to see if they make sense. Does it make sense to have 300 adult tickets? Well, it does if you have a 150 children ticket, because remember that one's going to be twice as much, and 50 senior citizen. And if you do some checking about the dollar amount here, they will add up to 3,025, and even more simply, if you just add them up, they add up to 500. I think we have a winner. Okay, the rest of these problems are yours as an assignment. Now remember, an assignment is graded. It's graded for correctness. You always want to try to do things correctly, but maybe even especially more on this one. And make sure that you follow similar to what I did, that you set up the problems, show your work, and then as you choose, you may solve the problems with matrices, with substitution, etc. I am going to add this to the directions. It should be in the directions, but I'm going to add it there. One problem, just one, you have to solve by hand. That means that one problem, you can't use Desmos. You have to use either a nice little substitution or elimination method. And I bet you're going to have at least one problem where you feel like you can do that. So that is going to be part of the requirement. All right. It's all yours.